Welcome back, one and all, to the 25th annual Putnam County Spelling Bee. We've reached our final round, and with just 2 spellers left, the competition's really heating up. And here it is, folks, our tie-breaking word, Q. Its language of origin, French. Definition, a line or sequence typically of people. Can we use it in a sentence? Sure thing. Why bother calling it a Q when you can just call it a line? And here's our potential champ up to the mic. If they answer correctly, victory is theirs. And they've spelled it Q. Just Q? The buzzer sounds, that's incorrect. A humiliating way to go out for our speller who forgot that the word Q isn't just spelled Q, but Q-U-E-U-E. How come? Who the heck knows? Hello, my darlings. Welcome to Class 3 of Unit 10, where we're talking about some Q's of our own in the form of linear functions. Now that we've built some familiarity with the vocabulary and notation of functions, we want to look at a couple different families of functions. And before we progress, let's regress for a little bit. Because of the functions we can encounter, the most simple among them are our linear functions. And the lovely thing about them is that everything we know about linear equations and linear relationships from Unit 4 still ports over. Now, in general, to write a linear function, I need to be able to use that function notation with my dependent variable f of x. But remember, f of x is really just a fancy way to say y. Well, what form of a line do we know where y is by itself? Take a look back at those notes. Tell me what you think is going to be on the other side of this equal sign. Go! 5, 4, 3, 2, 1, and stop. Well, if you guessed our iconic y equals mx plus b, that slope-intercept form, you would be correct. And again, we know these variables m and b are going to tell us some stuff about our line. Well, m is still going to represent our slope, which we define as the change in values of y, here represented by f of x, over the change in values of x, more simply, our rise over run, and b is still going to give us our y-intercept, the place where we cross the y-axis. Now, typically, we expect changing the value of x to change the value of f of x, but there is the off chance that at that value m, our slope, could be equal to 0. Now, if this is the case, what do you think is going to happen to our graph? Remind me, what do I end up with when my slope is 0? Go. And stop. Well, if m is equal to 0, hopefully you'll see that in that equation above, that mx term is going away. It's just going to be f of x is equal to b, which means no matter what x is, y is always b, so y is a constant value. Perhaps unsurprisingly then, we call this a constant function. And we know when y is by itself, right, x can be whatever it wants, but we're always the same place above or below the x-axis. This graph should give us a horizontal line. Beautiful. So now that we know how to define a linear function, we want to know how we can figure out if what we have on our hands is indeed linear. The first thing I want to know is when the equation of a function gives me a linear function. So, take a look back at your notes, or maybe just reference something in your mind palace. What's the criteria that an expression or equation, or in this case a function, needs to meet in order to be considered linear? Go. And stop. So you may remember, we said that in order for something to be considered linear, all of the terms containing variables must have a degree of 1. So here, all of the exponents that I see on each of my terms, right, they cannot be any greater than 1, and when I sum them all up in each of my terms, I get 1. See which of these equations down below meets this criteria, right? Which of these guys am I actually going to classify as linear? Go. And stop. Well, y equals x. Y has an invisible exponent of 1. x has an invisible exponent of 1, the degree of this guy is 1. It is indeed linear. Same thing for b, right? F of x is really just y, and y has an invisible exponent of 1. This 2x also has an invisible exponent of 1. This guy is linear. Now for c, hopefully you can immediately see this x squared is going to disqualify me. Here's a quadratic function. H of x equals 5 plus 3x root 7. Don't be thrown off by that root 7 at the back. The x still has an invisible exponent of 1. This guy is linear. Now for j of x, even though it looks like this x might have a variable 1, you may remember when we did our laws of exponents back in Unit 6 that when the variable is in the denominator, we actually have a negative exponent rather than a positive one. So this guy is not actually linear. You will learn eventually that this is an example of a rational function, which appears when you have variables in the denominator of a fraction. And last but not least, k of x is equal to 0. Well, here we know that this guy, it's just going to be constant, right? No matter what x is, I'm always going to spit out that y value of 0. Beautiful. Now that I know how to figure out if an equation is linear, let's take a look at some graphs. Now, you may remember from back in Unit 4 that the graph of a linear equation always takes the same shape. What would we expect the graph of a linear function to resemble? Go. And stop. Well, we should remember really well, the graph of any linear equation is a line. But there are a couple of criteria that we're going to put on this line. It can't just be any line. It has to be one line. So we'll say that it has to be a single line. It also needs to be a straight line, so there can be no bends or curves. And the last thing that we'll say, there's one type of line that cannot be a function. It cannot be a vertical line. Now take a couple seconds, pause the video. Why would a vertical line not be able to be a linear function, right? What from last class would it perhaps fail? Go. And stop. Well, hopefully, obviously, a vertical line would fail the vertical line test. So it is impossible for a vertical line to be a function. Based on these criteria here, can you tell me which of these guys are linear functions? Give yourself a minute, try it out, go ahead. Alrighty. Well, for A, this is obviously a parabola. This guy cannot be a linear function, even though it's a single curve and it is not vertical, it is not straight. Now for B, this guy is a single, straight, non-vertical line. This is absolutely a linear function. But for C, you'll notice here I have two lines, so it is no longer a single line. This guy is not linear. As we will see in a future class, this is actually the graph of an absolute value function. Beautiful. Now, my last way that I want to be able to figure out whether I have a linear function on my hands is by looking not at its graph, but at some of the points on its graph, which are often given to us in the form of a table. Now, there's an important relationship that I want us to notice here between our values. Here, I want us to fill out this table down below for each of the x values 0 through 7. Based on these inputs, there's something important that I want you to notice about the outputs. So do a little evaluating for me and tell me if you notice any patterns in those values. Go. And stop. Well, if I were to evaluate L of x when x equals 0, all I need to do is substitute 0 into my function notation. So I have 7 times 0, which is 0, minus 2 gets me an L of 0 equal to negative 2. Same thing plugging in for each of these. Here I would get 7 minus 2, which is 5. Here I would get 14 minus 2, which is 12. For 3, I would get 21 minus 2, which is 19. For 4, I would get 28 minus 2, which is 26. For 5, I would get 35 minus 2, which is 33. For 6, I would get 40. And for 7, I would get 47. Now, the important thing that I want us to notice here is that as our values of x increase, here every time that I move to the right, I go up by 1. what you'll hopefully see is that to get from each y value to the next, here I add 7 to get from -2 to 5. To get from 5 to 12, I add 7. To get from 12 to 19, I add 7. 19 to 26, I add 7, and so on. This shouldn't be a surprise, right? Because we know our slope is 7, and because we have that constant slope, we have a constant rate of change in the values of our function. And because we have that constant rate of change, we can expect what we call here the first difference, these sums that I've added here in orange down below, that first difference will always be constant in a linear function. With this idea in mind, do some first differencing here. Can you tell me, based on this pattern that all linear functions must follow, whether or not each of the tables below represent a linear function? Try it out. And stop. Well, for my table all the way on the left, to get from -3 to -1, I need to add 2. Same thing to get from -1 to 1. So same thing here, x is increasing by a constant amount. If it's linear, then y should also be increasing by a constant amount. Well, to get from 7 to 3, I need to subtract 4. From 3 to -1, I once again subtract 4. That first difference is constant. This is a linear function. Same thing for b here. To get from 2 to 3, from 3 to 4, I add 1 each time. So to get from 7 to 12, I add 5. To get from 12 to 19, I add 7. Here, the first difference is not constant, so this is not a linear function. And for c, to get from -6 to 1, I need to add 7. To get from 1 to 8, I need to add 7. As long as the first difference over here on the right is constant as well, I know I have a linear function. Here, notice I'm adding 0 every time, which is still constant. This here is a linear function, but it's going to be that special subtype of functions here. This guy is constant because our output value is always the same. Fantastic. So this is the main stuff I want us to know. And now just for a little bit of review, when it comes to linear functions, there are a couple of other things that we should be able to do as well. The first of which is identifying equations of lines. So I've got 2 criteria here. I want you to think back into that mind palace of yours, right? What are some strategies that we know? Given some criteria such as f of 0 equals 5, increasing x by 4 decreases f of x by 12, g of 4 equals 1, g of 8 equals 7. Try something out, right? See if you can find some equations of lines for me. And stop. Well, for f of 0 equals 5, we know that this notation is really giving us some points in disguise. If my input value of x is giving me that output value of y, then I know here that the point 0, 5 must be on my graph. Well, 0, 5, hey, x is 0. Isn't that my y-intercept? So there's going to be my value of b. And if I increase x by 4, what this tells me here is that x corresponds to run, right? So I have going up by 4 for my run, and then I decrease f of x by 12 every time that I run 4. So here that tells me that my rise should be -12, which means that my slope, represented as rise over run, should be -12 divided by +4, which is just -3. All I need to do now is slot these into place. Well, I know in general, my function notation is f of x equals mx plus b. Here, I know my value of m from up above, that's -3x, plus my value of b, which we've identified as 5. And now, let's take a look at our g function. So I know g of 4 equals 1. Once again, I can use this to my advantage here. This is really a point in disguise. If my input 4 gets me my output 1, then 4, 1, that point must be on my graph. Same thing here for g of 8 equals 7. That means that the point 8, 7 is on my graph. Well, in order to find the equation of a line here, remember that I need to use a fancy formula from back in Unit 4. What's the tool that I use to find some equations of lines? Look back in your notes. Tell me. Tell me! And stop. Well, here, all I need to use is my handy-dandy point-slope form. And my point-slope form, right, I remember, is y minus y1 equals m parentheses x minus x1. So if I can take these points here, the first thing that I need to do is find that slope and then substitute into my point-slope form to get my equation. Well, here, 4, 1, let's call this our x1, y1. 8, 7, let's call this our x2, y2. All I need to do now is plug into my slope formula, which is y2 minus y1 over x2 minus x1, find that value of m, and then use my point-slope form to get my equation. So here, y2 we've identified is 7, y1 is 1, x2 is 8, and x1 is 4. Simplifying here, 7 minus 1 is 6 over 8 minus 4, which is 4, and 6/4 reduces to 3/2. Now using my point-slope form, right, let me substitute. So I've got y minus y1, which up above we said was 1. I could use the other point, but here I chose that label, so I might as well stick with it. Equals our slope m, which is 3/2, times the quantity x minus x1, and x1 we identified up above as 4. Well, here, let me begin by getting rid of some parentheses. So I'm going to distribute that 3/2. So I've got y minus 1 is equal to 3/2 x, and then 3/2 of -4 would be -6. All I need to do now is add 1 to both sides to get y by itself. Here, y is equal to 3/2 x minus 5, which in our function notation, just swapping out here that y for g of x, because our equations above, or our points above, gave us that notation g for our function rule. Here, g of x should be equal to 3/2 x minus 5.